Hello everyone, I'm Jingyi Zhou. I'm a second-year PhD student from the Human Nutrition Department of the University of Alabama. Today I'm going to talk about the effects of fatty acid chemical structure on the complexation ability and physicochemical properties of starch-C18 fatty acid inclusion complexes. So starch is composed of amylose and amylopectin. Especially its amylose component is well known to form inclusion complexes with various small molecules. And when forming the inclusion complex, amylose will exist as a left-handed single helix to entrap the gas compound. So this is a well-known phenomenon. For instance, iodine solution is used to test the presence of starch by showing a purple-black color. This is because starch can form an inclusion complex with iodine. Also, lipids could form inclusion complex with starch, and many studies suggested that such starch-lipid inclusion complex is responsible for the soft crumb and anti-stalling properties of baked foods, as the formation of starch-lipid inclusion complex can retard its retrogradation. In addition, starch can entrap flavor compounds in the form of inclusion complex. By doing so, it may reduce the impact of aroma. And among these inclusion complex applications, starch-lipid inclusion complex has attracted much attention as a type of novel resistant starch. And the structure of the lipid gas is hypothesized to affect its complexation and properties, and thus affect its resistance to enzymatic digestion. So here in this study, we aim to investigate the complexation ability and physicochemical properties of high amylose maize starch inclusion complexes with 6 different types of C18 fatty acids with different degrees of unsaturation, including stearic acid, elytic acid, oleic acid, linoleic acid, alpha-linolenic acid, and conjugated linoleic acid. And among these 6 different types of C18 fatty acids, stearic acid is the saturated fatty acid. Elytic acid and oleic acid both contain one double bond. Linoleic acid and conjugated linoleic acid both contain 2 double bonds, and alpha-linolenic acid have 3 double bonds. So 2 methods were employed to form starch C18 fatty acid inclusion complexes, including the dimethyl sulfoxide method, which is the DMSO method, and also MTV helix method. So the formed inclusion complex were further characterized by complementary techniques, including X-ray diffraction, differential scanning calorimeter, and Fourier transform infrared spectroscopy. So first, let's move on to the DMSO method formed inclusion complex. So the starch was heated up to around 90 degrees Celsius together with the DMSO solution, followed by the addition of gas compound, which is our C18 fatty acid. And after that, the DI water was added into the starch gas solution, and then the mixed solution was cooled at room temperature for 24 hours to obtain the starch C18 fatty acid inclusion complex. First, the formed inclusion complex was characterized by DSC. The figure on the left is the DSC thermogram of pure C18 fatty acids, and the figure on the right is the thermogram for their corresponding inclusion complexes. In the DSC thermogram, if inclusion complex is successfully formed, an endothermic peak will be observed during heating, which indicates the dissociation of the formed inclusion complex. And from the left figure, we can see that stearic acid and elytic acid showed peaks at around 69 and 44 degrees Celsius respectively, which indicates the melting point of these 2 fatty acids, while no endothermic peaks were observed for other 4 types of fatty acids. Because oleic acid, linoleic acid, alpha-linolenic acid, and conjugated linoleic acid already present in liquid form under room temperature. And from the figure on the right, we can see that for all inclusion complexes, visible endothermic peaks could be observed within the range of 80 to 115 degrees Celsius, which indicate the successful formation of inclusion complex between high amylose maize starch and C18 fatty acids. The additional endothermic peak observed at around 69 degrees Celsius for the starch stearic acid sample was due to the melting of uncomplexed stearic acid in the sample. Among all the inclusion complexes, starch stearic acid inclusion complex had the highest dissociation temperature, which indicates the highest thermal stability. And from the figure, we can see that the thermal stability decreased with increased degree of unsaturation. In addition, although oleic acid and elatic acid both contain the same unsaturation degree, the trans structure of elatic acid increased its thermal stability compared to the cis structure of oleic acid. So such phenomena could be explained by the fact that the cis structure disrupts the linear shape of the fatty acid, while the trans structure resembles the linear structure of the saturated fatty acid. Furthermore, when comparing the linoleic acid to conjugated linoleic acid, the thermal stability of the inclusion complex was increased when the structure becomes conjugated, which is due to the presence of the trans double bonds in the conjugated dienes. Then the formed inclusion complexes were characterized by XRD. From the figure, we can see that all inclusion complexes showed characteristic V-type peaks at 13 degree and 20 degree, which indicate the formation of starch C18 fatty acids inclusion complex in a V6 type structure. And the XRD patterns support the DSC thermogram results, which confirm that the C18 fatty acid could successfully form inclusion complex with high amylose mid starch by using DMSO method. Lastly, the formed inclusion complexes were characterized by FTIR, and based on the figure, all of the starch C18 fatty acid samples exhibit peaks at wave number equal to 2850 and also 2920, with the starch stearic acid sample has the sharpest peak. And these two peaks correspond to the stretching vibration of the CH2 groups on the fatty acid chain. And the decrease in the intensity of the peaks as the number of double bonds increased could be due to less gas being encapsulated or fewer CH2 groups in the aliphatic chain. We next employed empty V-helix method to form starch fatty acid inclusion complex. And in this method, we first prepared empty V6H starch. And after preforming the empty V-type starch, the gas compound, which is the fatty acid, and different fractions of ethanol solutions were added. Due to the hydrophobic interaction, the fatty acid will be stabilized in the helical structure in order to form the V-type inclusion complex. Similarly, the formed V-type inclusion complexes were first characterized by using DSC, and figure on the left is the thermogram for V6H stearic acid inclusion complex. Figure in the middle shows the results of V6H elatic acid inclusion complex. And the figure on the right is the thermogram for V6H oleic acid inclusion complex. So for V6H stearic acid inclusion complex were formed under all circumstances. So two endotherms were observed with peak temperatures at around 69 degrees Celsius and 115 degrees Celsius, except the starch stearic acid samples with 100% ethanol solution, which actually showed endotherms with peak temperatures at around 69 degrees Celsius and 94 degrees Celsius. And the endothermic peaks around 69 degrees Celsius represent the melting process of stearic acid, indicating the presence of free stearic acid in the samples. For V6H elatic acid inclusion complex, a visible endothermic peak at around 115 degrees Celsius was found on the DSC thermograms for the samples with 40% ethanol solution. And the endothermic peak temperatures observed at around 44 degrees Celsius represents the melting process of free elatic acid in the samples. In addition, the samples with 60% ethanol solution showed two successive broad peaks between 80 and 115 degrees Celsius, which may indicate the presence of different V-type starches in the inclusion complex. While for the samples with 80% and 100% ethanol solutions, Different endotherms were observed with peak temperatures at around 115 degrees Celsius and 95 degrees Celsius, respectively. Among the starch oleic acid samples, one endothermic peak was found on the DSC thermogram of the samples with 40 and 100% ethanol solutions, with peak temperatures at around 95 degrees Celsius, which indicate the formation of inclusion complexes. While for the samples with 60 and 80% ethanol solutions, the low endotherms from approximately 80 to 110 degrees Celsius, with two broad peaks, could be resulted from the formation of different V-type starches. Similar as starch oleic acid samples, starch linoleic acid and alpha-linolenic acid samples with 60 and 80% ethanol solutions also showed low endotherms, with two broad peaks from 80 to 110 degrees Celsius. And starch linoleic acid samples with 40 and 100% ethanol showed one endothermic peak, with peak temperatures at around 95 degrees Celsius and 85 degrees Celsius respectively. Starch alpha-linolenic acid samples with 40% ethanol solution also showed a endothermic peak at around 95 degrees Celsius, while a broad endotherm from 80 to 105 degrees Celsius was observed in the starch alpha-linolenic acid sample with 100% ethanol solution, which could be due to the retrogradated amylopectin component in the high amylose maize starch. Then the formed V-type inclusion complexes were characterized by XRD. From the figure, we can see that stearic acid, ellatic acid, and oleic acid inclusion complexes all showed characteristic V-type peaks at 13 degree and 20 degree, which indicate the formation of inclusion complex in a V6 type structure. Also, a similar pattern was observed in linoleic acid and alpha-linolenic inclusion complex samples, which both showed characteristic V-type peaks at 13 and 20 degree, which indicate the formation of starch C18 fatty acid inclusion complex in a V6 type structure. And the XRD patterns support the DSC thermogram results, which confirms that the C18 fatty acid could successfully form inclusion complexes with high amylose maize starch by using empty V helix method. To conclude, all C18 fatty acids were able to form inclusion complex with starch by using either DMSO method or empty V helix method. And among all the formed inclusion complexes, stearic acid formed inclusion complex the most efficient. Also, based on our results, the chemical structure of C18 fatty acids could largely affect their complexation ability and physicochemical properties of the inclusion complex. And we also found that the thermal stability of inclusion complex will decrease as the degree of unsaturation increase. And the trans structure could actually increase the inclusion complex thermal stability compared to the cis structure. And for our future direction, we will conduct additional research to determine the effect of inclusion complex on digestion profile, which could eventually affect the digestibility and nutrition quality of starchy foods. So that's it. Thank you for listening.